Now that we've defined momentum and we've taken a look at how momentum relates to forces, we're going to talk a little bit more about momentum's conservation. We're going to take a lot of the ideas that we talked about in the first lecture and really kind of apply them to situations where we can use conservation of momentum to our benefit to find very simple answers for problems involving more than one object. So I'm going to start by saying that under certain circumstances, momentum is a conserved quantity. Just like we said that under certain circumstances, mechanical energy is conserved. The same kind of an idea comes to us for momentum. And when I say conservation of mechanical energy, you should be thinking, oh, situations where no non-conservative forces are working. And the same kind of thing happens here, only it's not non-conservative forces that we're worried about. We're worried about external forces when we're looking at situations where momentum is conserved. One of the examples that I'm going to use for us to consider conservation of momentum is a head-on collision of two billiard balls. So take a look at these two billiard balls. You have billiard ball A and billiard ball B moving toward each other. And they're going to collide and then they'll move away from each other. If we're going to say that momentum is conserved for this situation, there's a few assumptions we have to make. First, we have to assume that the net force for external forces is 0, which means that there's no large appreciable external force that is acting in this situation that would change either of these objects' momentum. So that means that these two balls would have to have a balanced force on a table. So for example, if they're rolling on a table, mg and Fn would cancel out to give them a value, to give it a net force value of 0. Likewise, if there's any small amount of friction, just like we said that mg didn't matter for the tennis ball getting struck, we could say that if this table is a smooth surface and there's a very low amount of friction, we should be able to still get a pretty accurate example, a pretty accurate estimation of change in momentum by neglecting that force. That means that the only significant forces during this collision are the forces of the balls exerting a force on each other. So that means that ball A is going to exert a force on ball B in that direction, and ball B is going to exert a force on ball A in that direction. And we're just going to assume every other net force, normal force, gravity, friction, any other forces that could potentially be acting, we're going to assume that those are pretty darn close to 0 or exactly 0. So the only forces that are acting during the collision is the force of ball B on ball A and the force of ball A on ball B. And if that happens, one of the things that we notice also happens is this is our momentum vector for ball A. This is our momentum vector for ball B. And we notice that after the collision here, the momentum for ball A has changed at least directions, if not directions and size. And the same thing could be said for the momentum of ball B. So that means that the momentum of each ball is going to change after the collision, change from however it was moving before, with what momentum it was moving with before, to the momentum that it's moving with after. So even though the momentum of ball A has changed from here to here, and the momentum of ball B has changed from here to here, we could say that the overall momentum of this system is a conserved quantity. So that means that the sum of these momentums, sum of momentum A plus momentum B before the collision, should be conserved, that total. So that means that this amount, momentum A plus momentum B before the collision, should be equal to the momentum A plus the momentum B after the collision, because a conserved quantity does not change. So let's go ahead and let's take a look at this. Let's break it down. So we're going to say that ball A, its momentum is given by mass of ball A times velocity of ball A. Ball B is given by mass of ball B plus velocity times velocity of ball B. And these are before collision values. For the after collision, the only thing that's potentially changed, as long as chunks of balls haven't flown anywhere, is the velocity of both ball A and B. And we represent the fact that these are after velocities by using this prime here. So that means that after the collision, the momentum is now mass of ball A times the velocity of ball A after the collision, MAVA prime. And after the collision, the momentum of ball B is given by the mass of ball B times the velocity of ball B after the collision, MBVB prime. We've said that if momentum is a conserved quantity, then the momentum of total momentum before the collision, adding this and this together, should be equal to the total momentum after the collision, adding this and this together. So that means that we have this equation here, MAVA plus MBVB should be equal to MAVA prime plus MBVB prime. Regardless of what the values are, if momentum is conserved, this has to be true because a conserved quantity does not change value. So that means that the total vector momentum, because remember, momentum is a vector quantity and it will have positives and negatives, so we're talking about vector addition here in our sums. So the total vector momentum of the system will be conserved. So let's go ahead and let's see that this is true using our good old-fashioned Newton's laws. So what we're going to assume to show that this is true is the same thing that we're going to assume every time we apply conservation of momentum. We're going to assume that the net force that we're calculating in this equation, F equals delta P over delta T, we're going to assume that that net force is just the force of the collisions. It's a ball-on-ball force, which according to Newton's third law, those two forces should be the same. And we're going to assume that the net force is equal to that force of collision, which means that we're neglecting any smaller external forces like friction in a situation like this where it's reasonable to do so. We're also going to assume that the force of collision for ball-on-ball collision is going to be constant during the change in time. So we're assuming that it's not a variable force, and that's actually an incorrect assumption, but one that we're going to make temporarily before we address why it's a slightly inaccurate assumption to make. So I rearranged this equation by multiplying both sides by the change in time, and I get that the change in momentum is going to be equal to the force times the change in time. And I'm going to apply this concept to ball B, which moves off to the right after the collision. So let's look. All right. When the balls collide, ball B moves off to the right. So it's given in the positive x direction. So if I apply it to ball B, then I'd say that the change in momentum of object B should be equal to the force that A exerted on B times the time. Because here's the force that A exerted on B, and it exerted that force for that time interval. I'm going to write out my change in momentum for ball B as MBVB prime minus MBVB, where the prime represents the after collision velocity. So that's going to equal the force that ball A exerted on ball B times the time interval that it happened over. So now we're going to do the same thing for the momentum of object A. And according to Newton's third law, one thing that we know is that the magnitude, the size of the force that each ball exerted on each other should be equal. But it should also be object. So that means that if we consider for ball B, the force that ball A exerted on it, we said that that was a positive force with a positive vector because it's in the positive direction. And that must mean that for ball A, it experienced a force from ball B that's the exact same size, but it's in the negative direction because it moved off to the left, and because Newton's third law says that the forces are an equal pair in magnitude with opposite direction. So I'm going to stick with this value right here, where I say the change in momentum A is equal to the force that ball A experienced as a result of ball B times the change in time. And then what I'm going to do is I'm going to say that the change in momentum is MAVA prime for after the collision minus MAVA for before the collision. And see this value right here, which was the force for ball A. And we said that the force for ball A should be equal in size to the force for ball B. So that means that I can actually plug in this value for force A as long as I flip the sign. So that means that into that equation I'm going to plug in a negative force B of A, which is the force that ball B experienced. But ball A experienced that exact same force, just in the opposite direction. So when I rewrite that, I say the final momentum of ball A minus the initial momentum of ball A equals negative the force that ball B experienced, because it was in the opposite direction, times the time interval. And if that negative force, but the force from ball B was equal to this quantity here, then I could set that equation equal to negative the change in momentum of ball B. So I dropped this out, I set these two sides of the equation equal to each other, and that's going to be MAVA prime minus MAVA equals MBVB minus MBVB prime. All right, where I flipped the signs because it's negative the change in momentum. That's this is actually equal to negative change in momentum for ball B, which is why those two flip-flop. I rearranged this equation just like I do for conservation of energy. I put the after values on the same side of the equation and the before values on the same side of the equation, and I get this equation where it says the momentum of ball A before the collision and the momentum of ball B before the collision added together vectorially is going to be equal to the momentum of ball A after the collision plus the momentum of ball B after the collision added vectorially. And it turns out that that equation that we looked at, by just saying that these are conserved quantities, so this must be true, we were able to derive it just by showing through Newton's first and second law that this has to be true. Conservation of momentum will work, and we can apply it to and use it for any two or more object systems that collide with each other. But we must be able to, in order to apply this, be able to neglect external forces. We need to be able to say that the net force for everything external, like gravity, like friction, like tension, anything else that's involved, we have to be able to say that that force is small enough that it equals 0. And so here's the law of conservation of momentum as it's written and as it would apply in that situation. The total momentum of an isolated system of objects will remain constant. So the total momentum of an isolated system is a conserved quantity. To further understand that, we're going to identify system, which is just a set of objects that we choose and that interact. So anytime you're choosing your system for a momentum conservation problem, or anytime you're choosing your system for an energy conservation problem, you just want to pick the objects that are interacting with each other, the objects that are colliding, the objects that are exploding, the objects that are moving toward or away from each other and plan to hit each other or interact with each other. That's your system. An isolated system, we're adding in this word isolated, and what we mean when we say an isolated system is a system where the only significant forces are the forces between the objects, Newton's third law forces between those two objects or three objects in the system. So what we're saying is that because of Newton's third law, right, if you have two objects colliding just like the billiard balls, right, this is going to be F A on B, this is going to be FB on A, and they're going to be equal but opposite. So if I added those two together, then the net force of the internal isolated system would be 0, and that's just because of Newton's third law. You can't have a force pair that doesn't have equal values in opposite directions. And then we're also going to say that the external forces have to equal 0, because if the external forces were a value greater than 0, then the momentum wouldn't be conserved, because of this equation that says that an external force would change momentum as long as it was acting. So if this value wasn't 0 or very near approximating a 0, then the momentum of the total system would not be conserved. It would be changed by that external force. So an example of this would be a rock falling as a result of gravity. Let's consider a situation where we define the system as just a rock. All right, if our system is only the rock, then what happens is a rock falls toward Earth. It has an initial velocity and it has a final velocity, and that occurs over some time. This is starting to look a lot like a kinematics problem. All right, we know that that rock accelerates due to g, which is downward at negative 9.80 meters per second squared. So we know that this rock is accelerating, and if the rock is accelerating, then that means that there's a force acting on it. And that force is not part of the system, because our system was just this rock. So this is a situation where momentum is not conserved, because our rock as a system all by itself is not isolated. However, if we consider our system to be the Earth and the rock, well, now we have a force pair. Here's the force of the Earth on the rock. Here's the force of the rock on the Earth. And those two forces by Newton's third law are equal and opposite, which means that if we neglect air resistance, now the net forces are equal to 0, and the momentum is conserved within the Earth-rock system because no external forces added up to change the momentum. So that means that as the rock changes its momentum, its velocity is increasing, making its momentum greater. That must mean that Earth is moving in the opposite direction toward the rock. So how come every time we drop something, we don't feel the Earth accelerating toward us? Well, consider here's the mass of the rock, and by comparison, not even to scale, there's the mass of the Earth. So if one of them is going to have a positive momentum, the other one's going to have a negative momentum, so that when we added them up, the momentum was conserved, then that means that the velocity change of the rock must have been very big, and the velocity change of the Earth must have been very small. In fact, so small that nobody was going to notice it. And we did discuss this concept when we originally talked about force pairs in Newton's third law, the fact that when the Earth is interacting, when the Earth is part of a force pair, that means that it too is accelerating due to Newton's third law, but because it's so massive, we never notice it. So, when we talk about the internal forces equaling 0, this is what we mean. This is a Newton's third law force pair, right? This force that the ball A experiences is a result of ball B. So this is the force of ball B on ball A, and ball B exerted that force in this direction. Here, this force is the force of ball A on ball B. This force is exerted by ball A colliding with ball E. This means that this force and this force are equal in magnitude, but opposite in direction. And here I give this one the negative value just because it's to the left, and conventionally we like to set our direction to the right as a positive direction. But that's Newton's third law. This is always going to apply for the internal forces in a system if they're interacting with each other. And for external forces, all we have to say is that the net force is equal to 0, or at least pretty darn close to equal to 0. So let's go ahead and let's look at an example where we could do a pretty straightforward calculation in this regard. We're going to take a look at two railroad cars that are colliding. We're going to say that railroad car A has a mass of 10,000 kilograms. and it's traveling at a speed of 24 meters per second. And it's going to strike an identical car, which means that this one also has a mass of 10,000 kilograms. And it's initially at rest, so it's just sitting there minding its own business. What's going to happen is at the moment of collision, the two cars are going to lock together. And that means that afterward they're going to move together, and if they're stuck together, it means their velocity is going to be the same. In fact, you can try this with a friend, grab their hand, try and move at different velocities. It's impossible. If you're stuck together, you must have the same velocity. So that will always be true. So we're going to calculate their common speed just after the collision, and we're going to use conservation of momentum to do so. So what we're going to say is that the moment before the collision, and the moment after the collision, that time interval is very small. So that means that because that time interval is very small, any external forces that could potentially be acting are likewise very small. So things like friction we're going to ignore, and we're going to say that, well, if we can say that the net forces of the external objects is equal to 0, or at least approximately equals 0, then momentum is conserved. So the momentum initially, the sum of the momentum initially, should be equal to the sum of the momentum afterward. So all I need to do is I need to establish what the initial momentum was, what the final momentum is made of, set them equal to each other, and solve for an unknown. Our initial momentum is given by MAVA and MBVB. Our initial momentum of MA, you have a mass of 10,000 kilograms and a velocity of 24 meters per second. For object B, you have a mass of 10,000 kilograms and a velocity of 0 meters per second, so that value is actually equal to 0. After the collision, you have MAV prime and MBV prime, where since they're stuck together, we know that their final velocity must be the same. When you see that their final velocity must be the same if they're stuck together, then you can automatically factor, and you could say MA plus MB times V prime. Another way to consider this is you could say, well, now that the two objects are stuck together, they are now just one bigger object that's equal to both of their masses. So let's go ahead and let's set initial and final momentum equal to each other. And I get MAVA equals MA plus MB times the final velocity, which is unknown. So I have 10,000 times 24 meters per second should equal 10,000 plus 10,000, 20,000 times V prime. I isolate my final velocity, and I can see that my V prime is actually going to be 1/2 the initial value, or 12 meters per second. Oops, sorry. So you can see that was actually incredibly straightforward, very easy to solve for in this circumstance. A system where if we'd been drawing free body diagrams and calculating it, for sure we would have gone through more steps. So considering situations where conservation of momentum is occurring, this is really, really nice. So you can do that. As long as there are no external forces acting on a system, the momentum is conserved, and you too can solve problems very simply just like that. Unfortunately, the real world has external forces. I know you were thinking that this is probably too good to be true. Oh, turns out maybe it's too good to be true. So the real world has external forces. There's friction on the billiard balls. There's friction in the railroad cars. There's gravity on a baseball causing it to actually move with projectile motion, as with the tennis ball. So what a huge bummer. Turns out momentum isn't conserved in most real-world situations when you have these other forces acting and the net force of the external forces is not equal to 0. So can conservation of momentum even be applied to anything that will actually make sense to calculate in the real world? Well, let's think about this. During a collision, when two objects smack into each other, the forces only act for a very small time. Even in a slow motion collision, there's a very small, brief amount of time for collision. Think about two billiard balls crashing. Think about two cars crashing together. The actual collision that occurs is a really small time interval. And the forces of one object on the other, the Newton's third law force pairs, are absolutely enormous. So that means that since the time interval is very small, the external forces are very insignificant compared to the huge interaction forces of the two objects colliding with each other. So that means that as long as we're only considering the briefest moment right before the collision and the briefest moment right after the collision, we can say that momentum is conserved just before and just after the collision, and the numbers that we get for that brief time interval just before and just after are going to be very, very accurate. So that means that you can use the idea of momentum as a conserved quantity for all sorts of really useful systems. Pretty much anything where you have two objects colliding, you're going to be able to apply conservation of momentum. And that means that we can use conservation of momentum for neat situations like exploding objects, like rocket propulsion, like the recoil of a gun, like the movement of a rowboat. So let's take a look at rocket propulsion just to begin with. What happens here is that a rocket, stationary in space, at least from our frame of reference, has a velocity of 0 and a momentum equal to 0. If momentum is a conserved quantity, then that means that the initial momentum has to equal 0. Then you get a rocket that burns some gas through a hydrazine interaction, and the gas moves backward and the rocket moves forward, and so you end up getting a final momentum of the rocket times the velocity of the rocket prime plus the momentum of the gas plus the velocity of the gas prime. And since momentum is a conserved quantity, we're only considering the moment before and the moment after. And you know in space there's no air particles, or at least such small air particles that we could definitely approximate external forces here equaling 0. And if we put it far enough out in space, then that means that the force of gravity is also likewise going to be incredibly small. So this is definitely a situation where conservation of momentum applies, which means that if I solved for this, it would be mgvg prime. In other words, the mass and the product of the mass and the velocity of the rocket, or the momentum of the rocket, should be equal and opposite vectorially to the mass of the gas and the velocity of the gas after that. So that means that a rocket can move through empty space just via conservation of momentum. It does not need to The gas does not need to push against the ground, nor does it need to push against a force of gravity, which means that this completely isolated system will be able to have acceleration, forward momentum gained by the rocket, and the rocket can accelerate in empty space. The rocket or the gas don't push against anything. They don't push against the air. They don't push against the planet. And that's all because of conservation of momentums. And that means that you can move something forward in space. And the same thing could be true for the recoil of a gun, right? Before you fire a gun, its momentum is 0. You pull the trigger, there's an explosion, the bullet moves forward, the gun moves backward, and the total momentum afterward should be equal to 0. If you're in a rowboat, and you decide to throw something out of the rowboat, if your rowboat was stationary initially, if the momentum was 0 before, and you throw something that way, then that means that you must move in the opposite direction just because your momentum must be conserved. And that's why it would be pretty foolish to decide to try and jump out of a boat and then turn around and dock it. You should dock it before you jump out. So let's go ahead and let's look at, these are all called explosion calculations or explosion collisions. Let's go ahead and let's take a look at the recoil on a gun. So for this example, we're going to say that the mass of the rifle is 5 kilograms, the mass of the bullet inside of the rifle is 2 kilograms, and the bullet itself, after the explosion, travels away from the rocket in a positive x direction at 620 meters per second. So before we shoot, bullets lodged in the gun, and both the bullet and the gun have a velocity equal to 0. So that means that their initial momentum should be equal to 0. After the collision, after the explosion, the bullet is moving to the right with a very large velocity and a momentum in that exact same direction. If the total momentum is still equal to 0, then that must mean that the gun likewise is recoiling in the opposite direction with a momentum that equals the same size but in opposite direction of the momentum of the forward momentum of the bullet. So that means that the total momentum at the end should be equal to the mass of the rifle times the velocity of the rifle prime plus the mass of the bullet plus the velocity of the bullet prime after the collision. And since momentum is conserved, we're ignoring temporarily just for the collision, gravity, friction, etc. Then that means that that should equal 0. So we can plug in mrvr prime plus mbvb prime, and that means that the mass of the rifle times the velocity of the rifle after the collision should be equal and opposite to the mass of the bullet times the velocity of the bullet after the collision. So if I want to know the recoil velocity, divide both sides by negative mr, and the recoil velocity of the bullet of the gun should be equal to mb over mr times vb prime. So that's going to be the mass of the bullet, 0.020 kilograms, divided by the mass of the gun, 5 kilograms, times the velocity of the bullet, 620 meters per second. Solving that, I end up getting that the recoil velocity of the gun is in the negative direction, 2.5 meters per second. And that's why you can get a bruise from shooting a rifle too much or not holding it tight against your body when you shoot it to change the impact velocity, because momentum is conserved in an explosion. So if the bullet moves forward, then the rifle must move backward. You can have less recoil if the bullet is smaller in mass compared to the mass of the gun, then the velocity of the gun on recoil will be less. So finally, let's take a look at a little conceptual example, falling on and off of a sled. So the question is, if an empty sled is sliding on a frictionless ice, when Benny drops vertically from a tree onto the sled, when he lands, does the sled speed up or slow down or keep going the same speed? So if Benny drops, then he's going to move down, and his velocity is going to be down in the y direction. He actually has absolutely no velocity in the x direction. That means that his initial momentum in the x direction should be equal to 0. But the initial momentum of the sled is the mass of the sled times the velocity of the sled. So the initial momentum is going to be 0 plus mv. The final momentum should then be equal to Benny on the sled. In other words, the final momentum is going to be equal to the mass of Benny plus the mass of the sled times the final velocity. So we set those two equal to each other. mv equals mb plus mv prime. And that means that the final velocity is going to be related to the initial velocity by this ratio, which shows that since the mass of Benny and the sled is larger than just the mass of the sled, that the final velocity must therefore be less than the initial velocity. In other words, when Benny dropped without any horizontal momentum onto the sled slowed down as a result, and that was to conserve its momentum. So now Benny's riding on the sled, and we're going to determine if, when he falls off the sled, does the velocity of the sled increase, decrease, or stay the same? And so in order to consider this problem, we're going to have to consider the very brief moment of the collision or explosion. The very moment that Benny steps off the sled, before he hits the ground, because when he hits the ground there's an external force, but before he hits the ground, right in the moment that he falls off, he has the exact same velocity as the sled. Think about your frame of reference. This is why jumping out of a car sucks. So since Benny has the same velocity and the sled has the same velocity, and the momentum here is mb plus m times v, and this, that's before, and after equals mbv, same velocity because he hasn't hit the ground or interacted with external forces, and mb and mv. And it turns out that mb plus m times v equals mb v prime plus m v prime, and where we can factor it, and if we factor it, then it turns out that v prime equals mb plus m over mb plus m times the initial velocity. So we show that as long as we're considering the moment before Benny's velocity is changed by an external force, that the sled should move away at the exact same velocity that it did before Benny fell off.